So first of all, I want to thank the organizers for inviting me to talk today. And so I'm a PhD student at the Laboratoire de Physique Théorique de la Matière Condensée, which is in Jussieu. And what I'm presenting today has been done in collaboration with my PhD supervisors, Jean-Noël Fuchs and Julien Vidal, as well as with Stephen Simon, which works in Oxford. And so how do I can you clean the screen? Yes. And now okay. Now so before I start with the actual subject, let me do a small recap of some quantum mechanics. So when you look at the quantum system, the space of all possible states in which this system can be forms the Hilbert space. And so every state inside of the space is a direction. Every state is a direction inside of this space. And to describe the quantum system, what you also need is the Hamiltonian, which is an operator which gives you the energies of the system. And this Hamiltonian can be represented as a matrix in the Hilbert space. So when you diagonalize the Hamiltonian, the eigenvalues give you the energy levels of the system, and the corresponding eigenvectors form an orthonormal basis of the Hilbert space. So on this picture, I just represented an energy spectrum. So you have different energy levels. The lowest energy level, so the lowest eigenvalue of the Hamiltonian corresponds to the ground state, and the other states are excited states, and they correspond to the presence of some excitations in the system. And it can happen that several eigenvectors correspond to the same eigenvalue, so then you have different states with the same energy. So for example, it's the case of that state. And then we say that this state is degenerate. And finally, when excitations can be localized in the system, then we can treat them as particles, and so we call them quasi-particles. And at zero temperature, the system is usually in its ground state, so there are no excitations, no quasi-particles. So in this talk, what we are going to be interested in is topological order. Topological order is a phase of matter. So phases of matter, so for example, the easiest examples of phases is liquid or solid phase, for example, for water. Then in condensed matter, you can also have ferromagnetic phase, antiferromagnetic phase. And so topological order is also a phase of matter, and which is usually studied at zero temperature. And so it appears in two-dimensional interacting quantum systems. And it has two very important properties, or characterizing properties. One is that the ground state degeneracy depends on the topology on which you put your system. So whether you put your system on a sphere, surface of genus 0, or you put it on a torus, or you put it on a two torus, the ground state degeneracy will be different. And the second defining property is that there are some exotic excitations, or quasi-particles, which are called anions, and which I'm explaining in this next slide. So to understand what anions are, we can look at exchange statistics of two identical particles. So we look at two particles like in this first picture, where one is located in A and the other one in B. And this two-particle state is described by a wave function, this psi AB. And now we're going to exchange the position. So the particle which was in B, we move it to A, and the particle which is in A, we move it to B. And through this process, the wave function gets a phase, so this e to the I theta. And if we do it again, so we move the particle which was first in A, now in B, back to A, and we do the same with the particle which was in B initially, we come back to a situation where, which looks like the initial one. but the wave function has acquired a phase which is e to the 2I theta. And this process is actually the same as just keeping one particle fixed in its position and going around once with the other particle. So that's what these two other pictures show. So now I keep the particle in A fixed and I move with the one in B to B prime. You see that this is exactly the same as if I had done just a position exchange, only a bit shifted in space. And then I move with the particle in B prime back to B. So this is as if I had done a double exchange. And looking at this is convenient because now we can look at the path represented by this dotted line. And what is actually important when we look at the phase acquired during this process is not how exactly this path goes, but just whether the particle is going around A or not. And so in 3 dimensions, you can see that we can always continuously deform this path into a point. So it's so we know that the final state when we have moved with B around A has to be the same as the initial state where we have not moved around A. And this means that this e to the 2I theta has to be 1. And so theta, we only have 2 possibilities. Either it is 0, and then we call these particles bosons. For example, photons, which are in the light, are bosons. Or theta is equal to pi, and then we have fermions, for example, electrons. However, if you are in 2 dimensions, so if we artificially restrict to 2 dimensions and some condensed matter systems, there are some more exotic behaviors which are possible, because then we don't have this constraint. We can't continuously deform this path into a path which goes not around A. So we don't have the constraint that this phase factor squared is equal to 1. And so actually any theta is possible. And that's why these particles are called anions, from any. And to be a bit more precise, there are actually 2 types of anions. So if the wave function acquires some phase during this double exchange, then we call them abelian anions. And in a more general setting, if you imagine that your wave function is at least twice degenerate, during this double exchange, you can also change from one state in this degenerate space to another state. And then we say it's non-abelian anions. So where does these anions appear in physics? So on the theoretical side, one motivation for studying it was a proposal to use it for quantum computation. So in regard of this, there have been some recent experiments made where they realized some topologically ordered phases in quantum simulators. And then they also appear in some physical effects like the fractional quantum Hall effect. And there's also been some recent experiments observing anions in this context. So there have been some, to describe these topologically ordered phases, they have some exactly solvable toy models which have been developed, which are defined on a lattice in 2 dimensions. We're going to be in 2 dimensions the whole talk. And so to name a few, the toric code model and the Kitaev quantum double model by Kitaev, the stringnet model by Levin and Wen in 2005, and the Kitaev honeycomb model, again by Kitaev. And all of these models build on concepts from lattice gauge theories, conformal field theories, topological quantum field theory, knot theory. And so in this talk, we are going to work on the stringnet model. Just to motivate a bit more what we're going to see in this talk. So the stringnet model is an exactly solvable toy model on a lattice, as I just said. And it is usually, so we chose the stringnet model because it is one of the most general ones from the model. It realizes a very large class of topologically ordered phases. And it is well studied, and it is usually studied at 0 temperature, where it has a ground state degeneracy as we expected for topological order, which depends on the genus. And so now we were interested to know what we can say about topological order in this model at finite temperature. Because, for example, when you look at experiments or in the idea of implement quantum computation, this is usually at finite temperatures. So that was our question. And to do so, we wanted to use a tool from statistical physics, which is the partition function, and which gives access to a lot of thermodynamic information about the system. And so this partition function can be expressed as the sum of the degeneracies of energy levels times exponential minus beta, the corresponding energy, where beta is the inverse temperature. And so you see that to compute this, this function, we don't need only to know the ground state degeneracy, but also the degeneracy of the excited levels. And so this finally brings me to the outline of the rest of the talk. So I will first describe the stringent model, and then I will explain how to compute the degeneracies of the energy levels, and also in particular of the excited energy levels. And finally, I will discuss the partition function. So to give a quick overview of the stringent model, the idea is that you give some input theory, you construct a lattice model with it and a Hamiltonian, and all of this is just a toolbox to generate some emergent phase, which is a theory which contains anions, so it's a topologically ordered phase. So first of all, what do we need as this input data? So we need a finite set of objects. I'm calling alpha, beta, gamma here. And these objects verify some fusion rules. So alpha times beta is equal to gives a sum, or can give a sum of different elements. And these fusion rules can be commutative. And they can have one or several outcomes. And so if we just have one outcome, we say it's abelian. And if there are several outcomes, we say it's non-abelian. Additionally, these objects have some dimensions. The alpha here, yes?
So when you say there is only one outcome, it's because this sum...
Yeah, it would be just 1n alpha beta gamma, which is equal to 1 and all others to 0.
So are these objects local on the lattice?
I did not say yet where they are on the lattice, but I will say it in a moment. So okay, the quantum dimensions also verify the fusion rules. And from these quantum dimensions, you can construct a total dimension, which is this DC defined here. And finally, you have some associativity rules on this fusion, which is given by the so-called F symbols. And all of this forms a unitary fusion category C. To give some more concrete examples, so the easiest thing you can do is to take the group elements of a group as objects. And in this case, the fusion rules are just the multiplication rules of the group. So in this case, your fusion rules are always abelian, because you always have just one fusion outcome. The quantum dimensions are all equal to 1. And so the total quantum dimension is just the square root of the number of elements in your group. And the associativity rules in this case are really just the associativity rules for the multiplication. A bit more complex, you can take irreducible representations of a group. And so in this case, the fusion rules are the tensor products of the irreducible representations. And there you see how you can get several outcomes, because if you take the tensor product of some irreps, you get a representation, which you can again decompose in a direct sum of irreducible representations. And the quantum dimensions in this case are the dimensions of the irreps. So they're integers, but they can be larger than 1. And finally, you can have even more general cases where these quantum dimensions can be irrational. And so to give just one concrete example, for example, the Fibonacci category, in which you have 2 objects called 1 and tau here. And so here I gave this, the list of fusion rules, and you see that the last one, this tau times tau equal 1 plus tau, this is non-abelian. So you have two different fusion outcomes, and you have the corresponding quantum dimension, which is irrational and which is the golden ratio. Okay, so now we have this input data, and now we are constructing the Hilbert space with it, so the space of configurations. And to do so, we take a trivalent lattice. For example, it can be a honeycomb lattice, as represented here. And where the degrees of freedom will be on the links. And so we will put the objects of our input category on the links, and they will define what values the degrees of freedom can take. And so that's how we construct the Hilbert space, but with one constraint. We will ask that at every vertex, the fusion rules are respected. So that means that if I take one vertex of the lattice and this first link is in the value, is in a state alpha, and the second link is in a state beta, then I want the third link to be a fusion outcome of alpha and beta. And so the Hilbert space is the space of all possible lattice configurations that verify the fusion rules at the vertices. And for a large number of vertices, the dimension of the Hilbert space grows proportionally to the total quantum dimension to the power of the number of vertices. So two more examples. So here for the group Z2, so we have two elements, 1 and S. And so on this picture, I decide to color the links which are in the state 1 in blue and the links which are in the state S in green. And so these four vertices are the only ones which will be allowed in the lattice because they correspond to the fusion rules. So for example, the first one corresponds to the rule 1 times 1 equal to 1. And the last one would be S times S equal to 1. And you see that some vertices do not appear, which could potentially appear. So for example, we don't have a vertex which is completely green because we don't have a fusion rule which is S times S equal to S. And just to give you an idea of how these states in the Hilbert space can look like, if you take a honeycomb lattice, so this first possibility, you color our links in blue or in 1, or you have just one loop of green, or you have a larger loop, or you have two loops, etc. So really every configuration you can have is a different state. And so again, the example of Fibonacci, in this case, we have one vertex more allowed because of this last fusion rule, which is tau times tau equal 1 plus tau. So this would be the 1. And this is the vertex corresponding to the fusion outcome tau. And so here we can do even more states because we also have these possible states where we have this vertex where everything is yellow appearing. So that's actually the reason why this model is called stringnet, because if you look at the links like colored as in colors, you can think of this as a yellow string, and the string is making a net. So you have some stringnet configurations. Yes.
Question from online audience.
Ah, okay.
The question is, should quantum dimensions satisfy any conditions?
They verify the fusion rules, but I don't know if this answers the question. Sorry?
The dimensions are integer?
Not necessarily, no. For example, for a Fibonacci, here you see it can be even irrational.
Is the difference between the Fibonacci and Z2?
So several examples, but for example, the quantum dimensions and the fact that here we have just abelian fusion rules, and in this case we have the last fusion rule, which is non-abelian. Okay, so now that we have built our Hilbert space, we can define the Hamiltonian, which will act in this space. And it is a sum of these operators BP So the sum goes over the number of plaquettes, because every BP will act on one plaquette P. And what it does is to modify the value of the degrees of freedom on the links around the plaquette P. Okay. And it has two important properties. First of all the BP operators commute with each other, which makes this Hamiltonian exactly solvable. And second of all, they are projectors. And so this leads to an easy interpretation of what these BP represent. They are projectors on the absence of excitation in the system or in the plaquette P. So if the eigenvalue of BP is 1, it means there is no excitation in the corresponding plaquette. And if the eigenvalue is 0, there is an excitation in the corresponding plaquette. And that's also why there is this minus sign in front of the Hamiltonian, because we want the ground state, so the state where all BP have eigenvalue 1 to be the lowest energy state. And so the ground state energy is very easy to find. It is just minus the number of plaquettes in the system. And then every time you add one excitation in a plaquette, you add 1 to the energy, so you have minus NP plus the number of excitations in the system. So like this. So what we know so far is just if we saw just the first line of the energy spectrum. So it is very easy because it is the distance between the energy levels is always the same, and it always corresponds to 1 excitation more. But the actual complexity and topological nature is hidden in the degeneracies, which we have not computed yet, and which we will see are more difficult to obtain. Okay, so finally, last step. Now we have seen, we have an input theory, which is this category C. We have seen how to construct a Hamiltonian, and now what remains to be described is how do we describe the anion theory, so the emergent phase. And actually, so this emergent phase is described by another category, which is the so-called Drinfeld center, a quantum double of the input category. So this is just to say that there is a mathematical way, which is called the tube algebra, was introduced by Okeneanu, to go from this input category to the output category, which will describe our emergent phase. So what does this category contain? So I will call it Z of C in the following. So it contains a new set of objects, and these objects are now going to be anions, okay? And a new set of fusion rules for these anions. Again, some F symbols, so associativity rules, some quantum dimensions, and we can define a new total quantum dimension from these quantum dimensions. And actually, this quantum dimension will be the square of the quantum dimension of the input category. So far, this data is exactly the same and very similar to the one we used to describe the lattice model. But since now we want to describe anions, and if you remember from the beginning, they were defined by some processes where we make them turn around each other and accumulate some phases. So we need some data which describes these processes, and this is given by the so-called modular matrices. So you have this matrix S here, this matrix element SAB describes how two anions A and B turn around each other. And the second matrix, the twist, explains how one anion rotates about 2 pi around itself. And so this is related to the spin of the anion. And finally, to describe this emergent phase, we need these the multiplicities NA. So there's one multiplicity for every anion type A. And these multiplicities are positive integers, and they are some data which comes about during the construction from C to Z of C. So it's not really a data from this emergent phase. It also depends on the input and so on the way you build your lattice model. And it selects which anions among all the objects of Z of C will actually live in the plaquettes of your system. So not all of the anions which we have seen just before, so all of these A, B, C, D, just a few of them will actually live in the plaquettes, and these NA tell us which of them. Yes. Okay, so you can't measure them. They are not in the plaquettes, but they, out of huge, maybe it will be a bit clearer later, but they can somehow appear without that you can measure them. They're not observable in the system, but they can, under certain conditions, still be there. And a last point about these multiplicities is that if the fusion rules of the input category are non-commutative, then they can be larger than 1. So they're always positive integers. Generally, they're 0 or 1. But if the fusion rules are non-commutative, they can be larger than 1. And this means that the corresponding anion, so you can see it as if it can exist in different subtypes in your system. So as an example, again, Z2. So the input category has 2 objects. The output, so the emergent phase has 4 objects. They're generally called 1, E, M, and F due to the analogy to lattice gauge theory. So, or maybe if you know the toric code, this is the same topological order as the one appearing in the toric code. And so the 1 corresponds to vacuum or absence of excitation. E corresponds to, is called like this because of electric charge. And so these are excitations which live usually on the vertices of the lattice in lattice gauge theory. And M would be the magnetic flux, which is located in the plaquettes. And F is a fermion, and it is the composition of a vertex and a plaquette excitation. And so the multiplicities here in the system where we have just excitations on the fluxes, they just select the vacuum, which can always exist, and the magnetic flux, so the excitation which is in the plaquette. And they do not select the excitations which have some part on the vertices. And so this is another slide to explain you the topological nature of these anions or quasi-particles. So as I already said, they are localizable in the plaquettes. So the 2 plaquettes which have pink in them, this means for these plaquettes, the corresponding BP operator has eigenvalue 0. And I always have to, they can never be created alone, singularly, one anion, because to create them, I have to change the value of one link. And since one link is always shared by 2 plaquettes, you will always create them as a pair. And this red line is to show which link has changed value. And then if I change other values of other links, I can move these excitations around in my lattice. And so this sort of explains the topological nature, that I can move them very far apart, but they will still be linked by some trace in the system, which is unobservable, but is there. And so if you want to re-annihilate them, you have to bring them back together if you want to make this trace in the system disappear. You can also move them around in another way and re-annihilate them like this, so bringing them back to the same plaquette. But then you have this red trace staying in the system. Somehow the system knows that they have been there. Okay, so now we are ready to describe the degeneracies of the system. So first of all, we look at the Guarnstedt degeneracy, which is a result which is known from the 90s and which was first derived actually in the context of topological quantum field theories and CFT, before even the stringnet model existed. And so see that there is a sum over all anions in this emergent phase, or in this the category describing the emergent phase, and it depends on the genus. So just in case you're wondering how this genus reappeared in the discussion, because so far all the lattices I drew were just on the plane, but the genus is because now you have to imagine that this lattice, you're wrapping it around some surface. So so you create boundary conditions and you So for example, on a torus or on a sphere or whatever surface you want. And so one property of this degeneracy is that it cannot be lifted by adding some local disorder. So it's really property of the whole system and topological in this sense. And well, since we have this sum over anions appearing, you can say that somehow this ground state knows what anions can exist in the model, although in the ground state we don't have excitations in the plaquettes. And this is linked to what I just said before, that you can create a pair of anion, you can move them around and reannihilate them, and you will have this trace remaining in the system. And so if this trace of anions remain is along a non-contractible loop, then the state with this loop is different from the state without the loop. And so on a sphere, there's no way you can do a non-contractible loop of anions. So you have no ground state degeneracy. On a torus, you can do as many of these loops as you have anions in your theory. So the ground state degeneracy is exactly the number of objects in Z of C. And then for a higher genus, you can do one loop around every, for every hole, you can do one non-contractible loop. But then you also have to tell how these loops fuse together. So it will depend also on the fusion rules of Z of C. And so it will be a more complicated number.
Sorry, I would see that for G equals 1, the 0 is the number of objects. Like, it's really the number of anions,
yes, and so the objects in Z of C are the anions.
Yes.
And with every anion, you can do a loop and it will be a different state.
But there might be more,
no? There can't be more. Okay, because
I see that there is at least the number of anions. But there might be more. So maybe some other thing.
No, because all other, so if you, for example, if you put two loops of anions, you can always fuse them together to one loop, and because you can't create the fusion rules are close in a sense, like you always get some anions in this category. So the most you can do is the number of objects. And again, so the same examples again. So if you take Z2, we have 4 objects in Z of C. And so on the sphere, we have no ground state degeneracy. On the torus, we have 4 corresponding to the 4 objects. And then we get some higher numbers for higher genus surfaces.
Sorry, can you also allow for surfaces with boundaries?
Yes, you can. I just don't discuss it in this talk, but it's not very complicated to generalize. And so for Fibonacci, we have also 4 objects in the emergent phase. So on the torus, we have the same degeneracy, but then because the fusion rules are different and the degeneracies depend on how you can fuse these anionic loops together, the higher genus degeneracies are different from the ones of Z2. Okay, and so obtaining the degeneracies for the excited states is almost the same, is similar to the obtaining ground state degeneracy, just that now you also add excitations in the plaquettes. And so most importantly, we have this multiplicity, which tells us which anions exist in the plaquettes. But also all other anions appear because they can exist as these closed loops, which are not observable. So only the NA selects which anions live in the plaquette and are observable, but all the other ones can appear potentially as some closed loops around non-trivial cycles. And you see that, okay, Q is the number of excitations. So if you set Q to 0, you see we recover the ground state degeneracy. And then the first factor is just a binomial coefficient, which tells you how you can place your Q excitation within your NP plaquettes. So now that we have, now that we have derived the degeneracies for the excited levels, we can obtain the partition function. And so we can, because we can express it as the sum over all different energy levels times their degeneracies. And so the sum goes from 0 to NP because Q equals 0 corresponds to the ground state, so no excitations in the system. And the most excitations you can put in your systems is the number of plaquettes, because you can put one excitation in every plaquette. And yes, so using our expression for the excited, for the degeneracies of excited levels, we arrive at this expression for the partition function, where you can see that it depends on the emergent phase, so on the anion, on the category describing the anions via the quantum dimensions, but it also depends on the input series, so on the way we constructed this model on the lattice via the multiplicities, on the topology of the manifold on which we place our system via the genus, and on the system size via the number of plaquettes, and finally also on the temperature via beta. And so to end with two examples of what we can do with this partition function. So we can determine the free energy. And we see that in the thermodynamic limit, when NP gets very large, it depends only on the total quantum dimension. So it does not depend anymore on fusion rules, for example, of the system, which means that different stringate models which have the same total quantum dimension behave similarly at thermodynamic limit. And also an interesting fact is that this is the same expression as for one-dimensional Potts model, where we would have dz colors when dz is an integer. So example, the Ising model when dz is equal to 2. And so from a two-dimensional quantum system, we get an expression which is similar to a one-dimensional classical system.
Sorry, this question, you explained it, but I forgot. So the total dimension is like the vacuum degeneracy, the total quantum dimension.
Not exactly the.
Sometimes, like in the context of 2D-CFTs, so one DCFT, it is called like G function or something like this. No, it is related. Even I'm not even sure if in 2D there is something like this. I think I don't remember what is the. I've seen many times this name quantum dimension in the context of 2D-CFT, but I cannot remember what is the definition, like whether it is related to what you are saying.
I'm not sure what I'm sure it is related, but I don't know what the quantum dimension is exactly in CFT. And finally, so we can also determine. Yes.
Can you just remind me how you compute it? Like
the total quantum dimension. Yes, it's the. I can just.
Sorry.
No problem. Sorry. It was defined by the sum of all the quantum dimensions of the objects in the category.
Dimensions are defined as like a singular. Each one is the piece basically.
I'm not sure of, so they arise as they are the. When you describe the fusion rules, you can describe them with these fusion matrices. And the quantum dimensions are the largest eigenvalue of these fusion matrices.
Okay, thank
you. Thank you. Thanks.
This is much.
Okay, so and then we can determine the specific heat per plaquette in the thermodynamic limit, which also just depends on the total quantum dimension. And we see that it is a smooth function of the temperature. It has no divergence, it has no singularities, and so we can say that we can see that there is no finite temperature phase transition in this model in the thermodynamic limit. So it means as soon as you switch on temperature, you lose the topological order. And so to conclude, so what we have seen is that the Stringer model is a lattice model which generates a topologically ordered phase, which contains anions and which has a ground state degeneracy at 0 temperature. Then we have obtained a general formula for the degeneracies of the excited energy levels for the Stringer model. With this degeneracy, we can obtain the partition function and some finite temperature properties. And so as someone asked, these results can be easily generalized to surfaces with boundaries, so disk, cylinder, etc. And so something else what we can do once we know the partition function is to compute some diagnostics of topological order at finite temperature. So for Wilson loops or topological entropy, topological mutual information. And one other generalization that one could do is to relax the vertex constraint. So in the lattice model, how we construct it, we impose the fusion rules at the vertices. But this is something that could, in theory, be violated. And if you allow these fusion rules to be violated, you can have excitations at the vertices. And so you can have, well, it would certainly change a bit these formulas. And so you have some models which allow this. So the extended Stringer model, for example, or the Kitaev quantum double model, or the Torrey code model. And with this, I have finished. Thank you.
Thank you very much. Thank you very much for the very nice talk. And are there any questions?
Yes.
So, are you expecting that there might be like phase transitions if you allow for vertex effects? Like, do you expect a qualitatively different behavior?
I don't think in the thermodynamic limit, but I know of, for example, there's an article which describes in the Kitaev quantum double model. So it tries to compute the mutual information, which is one way you can analyze whether there is topological order or not. And I find some scaling behavior so that for a certain size of the system and certain temperature, you can still have some topological order. And then if you go to the thermodynamic limit, you still lose it.
If you say before the thermodynamic limit in this model where we only have particles, well, quasi-particles.
I guess you can also find,
So
maybe you can also, so I don't think it changes deeply the physical behavior.
Like makes possible phase transitions.
Yes.
Yeah, I'm still having this question, but I think I should probably with myself. But so when you take just the free energy, in the so in the free energy, I guess so you should find that in the so in the thermodynamic limit it's basically dominated by the ground state, no?
Yes.
And so that ground state, and so in that limit, you should have that the object. I mean, somehow the object that appears is the ground state degeneracy. Somehow, I mean, it should appear there.
So when
Just because, I mean, if assuming that is the thing that I'm saying is actually correct, it's maybe.
But so the ground state energy depends on this degeneracy, but it was this formula, right? So it is a sum with the quantum dimensions of the different anions divided by the total quantum dimension.
Right. Okay. Okay, I think, okay, thank you. And any other question? So if not, we can thank Anna again for the very nice talk.